Okay, so good evening everyone. I am Shivani Dhok and I welcome you all to the first week tutorial for this course Introduction to Wireless and Cellular Communications. Okay, so since this is the very first week of this course, Few Logistics, every week on Saturday from 5 to 7 p.m. I'll be taking this tutorial. So plan will be like this. First, I'll discuss the content that is related to that particular week. So this is first week's tutorial. So all the questions will be related to your week 1 content. And after that, I'll solve some questions that are related to that week's content, as well as they will be little bit aligned to the questions that you get in your assignments. Obviously, those won't be your assignment questions, but they will guide you to solve your assignments. Then other thing, I have pinned a comment in the chat box that gives a link for my YouTube playlist. So after every week's tutorial, maybe within an hour or so, I'll upload this video to YouTube, and that you people can access quite easily. And that link will also be shared with you people by NPTEL. So they will create an Excel sheet and they will send you that particular link, um, in which there will be an Excel sheet in which you will have the link to this YouTube video as well as this slides, whatever I'll be using today. So if you prefer not to take notes, that is okay. You will be getting these slides from my side as well. I'll be uploading them just after this lecture. Then if this session is interactive, it will be good. That will benefit you more. And in general, please keep your mic on mute, but feel free to unmute yourself whenever you have any questions. Okay, so let's quickly start with this particular week content. So this particular week was a very general, high level overview of the wireless communication. Rather, it was like a motivation week, explaining why we need to study this particular wireless communication technology. So in this week, um, we focused on how communication systems were developed from 1G, 2G till 4G and 5G. Also, a little bit discussion was there, and then we looked at how the mobile devices were improved over years, how they got changed, a very primitive mobile device to the most recent mobile devices that we are using. Then other technologies that exist, wireless technologies such as Bluetooth, Zigbee, Wi-Fi, and all those things. Then multiple access techniques such as time division multiple access, frequency division multiple access, CDMA code division multiple access, OFDM, which has been used since 4G, 5G, and will be used till 6G as well. And some brief overview of 4G and 5G. So this was a very high level introduction. Not much of the technical content was covered in this particular week apart from link budget. Link budget also will be covered in much greater detail in the coming weeks once we look at link budget and cellular communication and all those things. So this week's plan is there are few basic things that are required or that are prerequisite for this particular course, which include the concepts like sampling theory from your signals and systems, then few things from your digital communication, which will be borrowed, or to the very basic things such as how do you convert a power to dB to dBW or dBm. So assuming the crowd is diverse, I will take things from for very basic this week. So in case you know things, please be patient for this particular week as I need to take care of a general crowd. Any questions till this point? Any questions regarding how tutorials are going to function or anything else before I move on to solve the questions? Okay. If there are no questions, then let me move on to the first section of the questions that I have planned. So let's start with the very fundamental course that as a prerequisite that is required for digital communication, that is signals and systems. And since we are doing digital communication, we are working with discrete sequences in time and discretization along amplitude as well, because we have digital signals. So let us first see how to sample in time domain. And a very nice theorem is given for sampling band limited signals, and that is the Nyquist sampling theorem. So what does that Nyquist sampling theorem say? So this Nyquist sampling theorem says that if you have a band limited signal, you have a band limited signal with maximum frequency as FM, then the minimum sampling frequency, or rather the sampling frequency, Fs, should be at least 2 times the maximum frequency. So this is the classical Nyquist sampling theorem that we have for, or that is given for a particular for a band limited signal. So this is the basis, and we'll solve a few questions related to this. Okay. So the first question says that find the Nyquist sampling rate for the following signals. So the very first signal given to us is x of t. This is the signal that is given to us. X of t is sine of 2 pi t plus sine of 4 pi t and sine of 8 pi t. So what we have to do, we need to first identify what is the maximum frequency in this particular given signal. Now this is summation of sinusoids, and sines or cosines are in their general form are written as sine 2 pi ft, or we have cos of 2 pi ft, where f is the frequency of that particular sinusoid. So if we write this particular signal, each component of this particular signal in this form, in the standard form, the first thing that we can write is, so we have x of t as sine 2 pi 1t plus sine 2 pi 2t plus sine 2 pi 4t. So the maximum frequency in this particular setup it depends on this particular term, which is 4. So the maximum frequency in this signal, so maximum frequency FM is 4 hertz. So therefore sampling frequency minimum Nyquist sampling rate. Okay, so this particular thing is your Nyquist sampling rate. It is the minimum sampling rate that you can use. It's 2 times FM, which is equal to 8 samples per second. Okay, is it clear? This is very basic thing from signals and systems, but still it's good to revise few concepts before we dig into wireless systems. Okay, let's move on to the second part of this question then. So the second part of this question is x of t is equal to sine square 8 pi t. So this is square of a sinusoid, and we are used to things like sine 2 pi ft, cos 2 pi ft. So let us first use this identity, sine square theta, which is equal to 1 minus cos 2 theta by 2. So using this, what do we get? We get 1 minus cos of 2 pi 8t by 2. I can write this as half minus half into cos of 2 pi 8t. So here this half is essentially a DC component, and the frequency of a DC component is 0. And this thing is an AC, or this has some frequency, and the frequency of this particular sinusoid is FM, which is 8 hertz. So therefore, what do we have? Therefore, maximum frequency is 8 hertz. Therefore, sampling frequency is 2 times FM, which is 16 samples per second. So this sampling frequency gives you an idea of how many samples you are going to generate in 1 second. Or if you have a sinusoid, then in 1 second, how many samples are you going to collect for that particular signal? Okay, so that's why the unit of the sampling frequency, many people refer to it as hertz, but it is essentially samples per second. Okay, let's quickly move on to the next part. So the signal now given to us here is x of t is summation n running from 0 to n cos square 2 pi nft. So to simplify this, we can use the identity cos square theta is 1 plus cos 2 theta by 2. So therefore, what we get, x of t is summation n from 0 to capital N 1 plus cos of 2 pi 2n f t whole divided by 2. This is equal to n plus 1 by 2, which comes from this 1 plus half of summation n running from 0 to n cos of 2 pi 2n f. So again, similar to the previous part, this is a constant and this is a DC component. And this summation here is basically summation of lots of sinusoids, but the maximum frequency in this particular sinusoid will be when this little n takes the highest value. That is, this little n is equal to n. So this will have, this part has the maximum frequency as 2nf. Let me add a page. So therefore, maximum frequency in this signal that is FM, is 2NF. Therefore, Nyquist sampling rate that is 2 times FM, that is 4NF. This was in hertz, this will be in samples per second. Any questions in this particular Nyquist sampling rate part? This was the last part of this first question. If you have any questions in this thing, let me know. Okay. If there are no questions, then let's move on to the second question. And in this particular question, let's uh, add one more layer on top of the sampling, and that is your quantization. So what do you mean by quantization? So you have a continuous time signal. Let's do it in this way. Okay. So you have a continuous time signal, something like this, let's say. And so this black one is your and then when you want to do your sampling or want to get discrete time signals, what you do, you sample at after some duration of TS. So let's say, just for the sake, let's say let's do it this way. Okay, so let's say we sample at t equal to 0, then we'll sample at TS, 2TS, 3TS, 4TS, something like this. And so on. So we'll continue to do this. So this is TS, then 2TS, 3TS, and so on. TS is what? TS is your sampling duration. And this is 1 over Fs, where Fs is your sampling frequency. Now in your digital communication, you don't have infinite precision because you are going to process it digitally. Your computer systems or whatever operating systems that you are going to deploy, those are digital in nature. So amplitude also can't take infinite precision. So right now what is happening, we have the amplitudes, after sampling in time, we get the amplitudes that are correspond actual amplitudes and with infinite precision. So obviously we can't have all of these amplitudes. So the after sampling, what we do, so these pink ones, pink markers, circle markers, are basically your discrete time samples. And the way we sampled in the time domain, we now sample in your amplitude direction as well. So let's say we have one here, then let's say we sample quantize like this, something like this, 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 So we have something like this. So these are different quantization levels. So these gray ones are quantization levels. And for this so what we will do is the nearest point, so let's say this sample where um, we'll assign that particular quantization level which is closest to this particular thing. So for this we have this part as the quantized value, then for the second one we have this one, for third one also we have this one, then for this we have this one, then this overlaps, then we have this one, then here, here, something like this, like this, like this, we have here and here. So these purple ones are quantized samples. So right now what I have shown is something known as uniform quantizer. Like each quantization level has a difference of delta. There are other efficient ways of doing this quantization, but I'm not going into details of that right now. That can be looked at from your previous courses. But this is the basic idea of quantization. So you bring in finite resolution in your system instead of your infinite precision that you get just after sampling. So what happens is you have a continuous time signal, you sample it in time, you sample it in frequency, in amplitude, and then you get your quantized signals, and then you assign bits to those quantized signals and you transmit those bits. So the question that now is asked here is, consider a band limited signal with bandwidth 15, with one-sided bandwidth as 15 kilohertz being sampled at twice the Nyquist rate. Suppose it is quantized using a uniform quantizer, which is exactly the thing that we have in this particular figure, with 256 levels. So these gray lines, the number of these gray lines are 256. Then find the data rate of the quantized signal. Okay, so this is a big question. Let us break it down in parts. So what is given to us is, first thing given to us is, consider a band limited signal with one-sided bandwidth of 15 kilohertz. So just for illustration, how does a band limited signal look? So you have this frequency axis, and if I plot the Fourier transform x of f of this particular signal, it is limited within a band, something like this, and it is zero everywhere outside this particular band. So this signal is limited only to this particular band, and hence it is known as a band limited signal. So this band limited signal has the maximum frequency, which is FM, as 15 kilohertz. Okay, so the maximum frequency of signal FM is 15 kilohertz. Then it is given that this particular signal is sampled at twice the Nyquist rate. What is Nyquist rate? Nyquist rate is the minimum sampling frequency that you can use for that particular band limited signal, and by Nyquist sampling theorem it is equal to 2 times FM. Okay, but instead of sampling at this rate, we are going to sample it at twice the Nyquist rate. So therefore the sampling frequency that is Fs is 2 times the Nyquist rate. That is 2 times 2 FM, or rather 4 FM. And what is the value of your maximum frequency? 15 kilohertz. So 4 into 15 kilohertz. So this turns out to be your 60 samples, kilo samples per second. Okay. Now let's go back to this diagram. Okay. When you are sampling, you get, so sampling at one instant gives you one sample. At second instant gives you another sample. So when you are saying that you are getting 60,000 samples per second, it means that in 1 second you get 60,000 such pink markers, pink circle markers. So you, and what do we say? Each of this pink marker is associated to one quantization level. So what is the system? So in 1 second, 60,000 samples are obtained. Then each of this sample is associated to a quantization level. Okay. Now what is given to us about quantization level? Suppose it is quantized using a uniform quantizer with 256 levels. So the number of quantization levels this is equal to 256. Okay. And then what is said? Find the data rate of this quantized signal. Okay. Now data rate is generally in either kbps, kilobits per second, mbps, megabits per second, or bytes per megabytes per second, kilobytes per second, and so on. Which means that we need to first understand how do we associate this number of quantization levels to the number of bits that are used to associate bits to get these quantization levels. Okay. Okay. So let's say we use m bits for quantization. Then this will lead to 2 to the power m unique combinations. Then these quantization levels are also unique, these 256. So if I'm using m bits, then this 2 to the power m should be at least equal to this 256. So you should have L to be equal to 2 to the power m, and therefore this m turns out to be equal to log L to the base 2. So what do we have? And in general we use a seal. We will, if L is not 2 to the power something, we'll have to use higher number of bits. So here we'll have log 2 250 log 256 to the base 2, which is log of this is 2 to the power 8. So this comes out to be equal to 8 bits. So what do we get from this discussion? The quantization levels can be represented using 8 bits. So every quantization level can be associated using 8 bits. Okay. Which means that what do we have? Every sample is associated to a quantization level, and every quantization level can be represented using 8 bits, which means that each sample can be represented using 8 bits. Okay. Now we understood how this quantization and the bits can be associated. Now the main question that we need to answer is find the data rate of the quantized signal. What do you mean by data rate? So data rate is number of bits that you either generate or you transmit per second. Okay, this is the uh, basic definition of your thing, data rate. So this we can simplify as number of samples that we generate per second into number of bits that are required per sample. So the first thing that we have is nothing but your sampling frequency. And this is the number of bits required for quantization. So this is number of bits used for quantization. Okay. So sampling frequency was what? Sampling frequency was 60 kilo samples per second into number of bits was 8 bits per second, 8 bits per sample. So this turns out to be equal to 480 kilo bits per second or kbps. Is this okay? Any questions at any of these steps? Any doubts in what do you mean by quantization, sampling, data rate? What exactly is happening in this business? Please feel free to ask.
Hi, ma'am. I have one question.
Hmm. Yeah, go ahead.
If you go about in sampling, yeah,
Yeah.
here.
Hmm.
So 2 into 2 FM. This one, I like already
Okay.
Nyquist rate of per Nyquist 2 FM, correct? It's 30.
Right.
Then
Right.
directly that will come. Now, why 2 into 2? That I didn't get.
Okay. So now go back to the question that we have. So it says that this particular signal is being
Twice
sampled
the
at
Nyquist.
twice the Nyquist rate.
Got it, ma'am. Got it. Okay,
Okay.
understood. Understood.
Yeah.
Yeah, thank you.
Any other questions? Okay. If there are no questions, then let me move on to the next question. So before that, let me again bring in some basics. So now I'll quickly discuss a very basic concept which I believe everyone might be knowing, but just for the sake of completeness, and many people don't know it also. So when you have a power, so power in linear units, when you have a linear representation of power, its units are watts, and this you can convert in logarithmic units, which are in two logarithmic units. One is dBW or dB watts, and another is dBm, that is dB milliwatts. So what changes from dBW to dBm is the reference power that we are going to use. So how do we calculate these two? So power in dBW is given by 10 log power in watts to the base 10, and power in dBm is given by 10 log power in to the base 10. Okay, so the difference is in the reference um, power that we are looking at. So in the first one we are referring considering power in watts, and in the second one we are referring power in milliwatts. So dBW, W corresponds to watts, and dBm, M corresponds to milliwatts. Now this dBW and dBm can be related to each other by a shift. So that can be simply derived something like this. So we can write this as power in milliwatts. We can simply write as power in watts into 10 raised to 3. Okay, so this becomes 10 log to the base 10 power in watts plus 10 log to the base 10, 10 to the power 3. So this comes out to be equal to power in dBW plus 30. So what we will do is we'll just focus on this particular part, that is dBW, and then we'll just use power in dBW plus 30 to get dBm values. So this entire thing is basically in dBm. So based on that, I have taken too many examples for this because I want you to get used to this concept a lot. Because when you go in the subsequent lectures, some calculations will be in decibels, dB scale, some calculations will be in linear scale. In general, if you have the very basic generic formula, you need to look into it with the help of linear scale always. But there are some places where we are going to explicitly use dB calculations, and those will be most probably related to your link budget calculations. Link budget, then SNR, signal to noise ratio, and all those things. So when we go ahead with the time, you will see when these dB and when this dBm things show up. Okay. Okay, so first part, convert the following transmit powers to dBW and dBm. The first one is 10 watts. So let's start with the basic thing, that is dBW. So your power in, I'll just use P for power, in dBW is 10 log 10 to the base 10, which comes out to be equal to simply 10 dB, and power in dBm is essentially this power in dBW 10 plus 30, that is 40 dBm. It is as simple as that. Just a minute, give me a moment. Okay, yeah, sorry. Okay, so we have this. Let's move on to the second part. This is dBW. So power in dBW, you have 1 milliwatt. So you have 10 log to the base 10. You have 1 milliwatt, so that is 10 raised to minus 3 watts. So this is nothing but your 30 dB, minus 30 dBW, and this in dBm is minus 30 plus 30, that is 0 dBm. Now if you go back to your definition for your dBm thing, so your power in dBm, you can write it as 10 log to the base 10, your power in milliwatt, and in milliwatt this is essentially 1. So this comes out to be equal to 0 dB. M. Yeah, M. Okay. This might be a boring exercise, but yeah, it's okay. It's good to do it once. Okay, so the third one is your 100 watts. So your power in dVW is 10 log to the base 10 100. So this is equal to 10 log to the base 10, and you have 10 raised to 2. So this is nothing but your 20 dBW. So one thing to know, come from this particular point is when you have 100,000, 10,000, and so on, you start to see dBs such as 10 dB, 20 dB, 40 dB, and so on. So if someone says you that you have 20 dBW of power, it corresponds to 100 watts, which is huge, which is very huge. Your phone transmits in milliwatts. And in dBm, this is 20 plus 30, that is 50 dBm. Similarly, when you have 20 watts, this is 10 log to the base 10, 20. Now for this you will need calculators. You can use it. You will be given calculators, digital ones, in your exam as well. So that's okay. And in dBm, this is 13 plus 30, that is 43.01 dBm. One thing, when you will use the calculators, be careful. This is not the natural log. This is to the base 10. So carefully choose the function that you're going to use, or the operator that you're going to use in your calculators. You'll do entire calculation correctly, but at the end, if you use a wrong base for your logarithm, you will be off by a lot. And these exam people who will set the paper, he will know at what level students can make mistakes. So obviously, you will find that particular solution in the options. Okay, 15 watts. So in dBW, this is 10 log to the base 10. 15. This comes out to be equal to 11.76 dBW, and this is equal to your 41.76 dBm. Then this 2 watts is something interesting. So this 2 watts is 10, okay, so I'll write it in this way. 2 watts is 10 log to the base 10 2, and this comes approximately equal to 3 dB. And dBW, and this is equal to 33 dBm. I'll come back to this 3 dB thing soon. Then this my 0.5 watts is 10 log to the base 10, 1 by 2. 0.5 is 1 by 2, which is nothing but minus 10 log to the base 10 2, which is again minus 3 dB. But dBW, and but this is 27 dBm. And when you have 1 watt, 10 log to the base 10, sorry, 1 watt is 10 log to the base 10 1, which is equal to 0 dBW, and which is equal to 30 dBm. Okay, so now 1 watt corresponds to 30 dBm, 0 dBW. When you had 2 watts, you are getting 3 dBW. So when you multiply or you double your power, you get a 3 dB gain. So if you subtract this 3 from this 0, sorry, the 0 from that 3, so you get a 3 dB difference. So when you double the power, you get a 3 dB ka gain in your system. Similarly, you have minus 3 dB here, which corresponds to 0.5. If you multiply 0.5 by 2, you should get again a 3 dB gain. So minus 3 plus 3 corresponds to 0. So that is the thing that you get, that is 0 dB W. Okay. Is it clear? So when you double anything, you get a 3 dB gain. That is a takeaway that you should take from this particular thing. This might be known to you, but it's important to keep in mind because many times these calculations can be done quickly. Okay, there are no questions, then let me move on to the next question. Before going ahead with the next question, I'll again introduce a basic concept of digital communication that has been there or that you might be knowing, but still I'll just give a quick recap. So if we go back to our thing here, quantization. So we had a continuous time signal. What we did, we sampled it in time. Then we got the discrete time samples. Then we quantized it in amplitudes, and then we associated each of these quantization level to a particular number of bits. So after doing all of this business, what we are going to see is a sequence of bits. So we get some sequence of bits. Then in your digital communication, what do? You apply channel code, you apply source coding for reducing the number of bits, and then you apply channel coding to improve, to add some redundancy in order to have some error correction. And after that, again, what you get is a sequence of bits. So we get in digital communication, what we want to transmit is a sequence of bits. So we have a sequence of bits. Let's say 0 1 1 0 0 1 and so on. So you get a sequence of bits. But how do you transmit it? For transmitting it, you need to mount these bits on some waveform, some analog waveform, some carrier frequency. Okay. And to do that, what do? First, we group these bits into, let's say, a length of k, something like this, and so on. And from these k bits, you get small sequences. So if you have 4 bits, so if k is 4, then you will get 2 to the power k unique combinations of bits. And to each of these unique combinations, you associate a waveform. Associate a waveform to each, or associate a unique waveform to each of these combinations. And these waveforms lead to something known as constellations. For example, you might have heard about BPSK, QPSK, and all those things. So what do? You have a sequence of bits, you combine those sequence of bits, and then you get sorry, yeah, and then you get 2 to the power k unique combinations, and to each of these unique combinations you assign a unique waveform, and that waveform you use to transmit to your signal, your information. Now, I won't go into details of this. This is there in your digital communication. I will recommend you to go and look in ProKISS book, where they give a nice signal space representation of constellations or any of these digital communication signals. It's nice to go through that concept once, but any point in constellation. So each of these waveform, this is a continuous time waveform, but you can get an equivalent vector representation of it. Okay, so if I have 2 to the power k possibilities, that is m equal to 2 to the power k possibilities, then for every mth symbol, or these combinations of bits, or these combinations are essentially known as symbols, every mth symbol will have some dimension. Can, let's say, sm can be represented using a vector sm1, sm2, and so on till smn, where n is the dimension of this particular vector. Okay, and this is how we get it. Then every symbol will be associated with energy. So this em is basically the energy of the mth signal, and this is given by the Euclidean norm, or in other words, this is basically sm1 square plus sm2 square and so on till smn square. This is nothing but the Euclidean distance of this particular vector from origin. And it might happen that these sequences don't occur with equal probability. For example, this particular sequence might occur too frequently compared to this particular sequence. That might be the case. So there is a probability with which a particular symbol might get generated. So let's say PR of m. So probability of mth symbol. Okay. So now what are we interested in? So this particular constellation will have an average energy or average power. So this average energy of this constellation is given by summation I equal to 1 to capital M, little m. Little m equal to capital M, probability that you are transmitting this particular signal symbol Sm into its energy. So this is your average energy of the constellation. This is a basic concept that is covered in digital communication. I have made a huge jump from here to here because that is a prerequisite, but you can refer to ProKISS book for this particular setup. It explains very beautifully this particular signal space representation, how you associate a waveform, the very generic way of assigning a waveform, and so on. Okay, so now let's move on to the question that I want to solve. So find the average symbol energy for the following constellation, assuming all the symbols are equiprobable. So what is given to us, that all the signals or probability of are equiprobable. In other words, the probability of mth symbol is 1 by m, and here we have 8 such symbols. So this is 1 by 8. for all m. Okay, now how can you get your sm from this? So we have this sm kind of representation, right? A vector. How to get it? So let us start with this particular thing. You have s1, which I can write as, just look at its coordinates. So its coordinates are basically a comma 0. So this is your s11 and this is your s12 vector. Similarly, this particular thing is a by root 2 into a by root 2. Then you have 0 comma a, you have minus a by root 2 into a by root 2. Then you have minus a comma a, minus a comma 0, sorry. Then you have minus a by root 2 into minus a by root 2. Then here you have 0 comma minus a, and here you will have a by root 2 comma minus a by root 2. So you have different SMs here. So let us now apply this particular formula. Probability of average energy of constellation is this. So average energy this is summation m equal to 1 to 8 and you have Sm squared into probability of the Sm. Now this Sm square is what? This is basically the squared Euclidean distance of Sm from origin. Okay. What do you mean by Euclidean distance? The normal under root x square plus y square distance that you have. And you see that all of these points lie on a circle. So the Euclidean distance of all of these points is same with respect to the origin, and that is nothing but the radius of the circle, which is a. Okay, so if you take under root a square plus a square under a square of this quantity plus square of this quantity, that will be a square by 2 plus a square by 2, which is a. Similarly here the square distance is a square. Similarly here the square distance is a square, and so on. So in this particular setup we have Euclidean distance squared of every symbol to be equal to the radius of your circle squared, that is a square, and this is for all m. And this particular setup, when you have everything on a circle, and what changes from one symbol to another symbol is only the phase of the symbol, is referred to as phase shift keying constellation. So this is a classic example of phase shift keying constellation, or rather PSK. And how many points do you have in this constellation? Those are 8. So we refer to this as 8 PSK. In general, you will have MPSK, where M will take values like 2, 4, 8, 16, and so on. Okay, so let us plug in the value of, uh, yeah, okay. Okay, so let us plug in the value of the Sm square in this, in your average symbol energy. So therefore, average energy is summation m equal to 1 to capital 8. Then here we have Sm square as a square into probability of every symbol is 1 by 8. So this comes out to be equal to 8 square by a square by 8 into 8, that is a square. So for an MTSK type constellation, where all the constellation points are equidistant from the origin, we have a uniform distance from the origin. In these kind of setups, average symbol energy and the energy of every symbol is same. So that is one of the nice property of this phase shift keying constellation. So even if you don't have equiprobable symbols, then also, so even when symbols in in PSK constellation are not equiprobable, we have norm of Sm squared to the A squared. So therefore, your average energy is summation m equal to 1 to m. Let's say you have general m points into Sm square, norm Sm square, that is A square, into probability of Sm. So this A square is independent of m, that comes outside, into summation m running from 1 to capital M probability of Sm, and summation of all the probabilities is 1. So this again turns out to be A square. So this is a nice property of this PSK constellation. So even if you don't have equiprobable symbols, then also your average energy, average symbol energy is equal to the energy of every symbol in your PSK constellation. This property is not true for any other constellation, whether you go for your pulse amplitude modulation or for your quadrature amplitude modulation or any other thing. I hope this is clear. So every question I'm trying to bring some new insights and revise the basics that were covered in the digital communication course. Okay. If there are no questions, then let me move on to the next question. You have to calculate. I don't remember. It depends on how you are putting your constellation and everything. So I'll give you a general case for a given constellation, how to do it, and maybe you can take up the 8-bit QAM. You are asking for 8-bit QAM. So 8-bit QAM will have 2 to the power 8 possibilities. You don't have a general formula for that. Or rather you have it, just plug in the values. It will be there in Procus. So I'll not take QAM, but I'll take something that is similar to QAM, which has changes in amplitude as well as phase. Okay, so this is the given constellation and we have to repeat the same exercise that we did in the previous question. The only catch here is the constellation points are not equidistant from the origin, and second, they are not equiprobable. For example, this particular constellation point occurs with probability 1 by 12. This particular constellation point occurs with probability again 1 by 12. However, this particular constellation point, this one, these occur with probability 1 by 18. So now we'll have to rely on the basic formula that we had seen earlier. So let me first write down the probabilities that, or the vector values. So this point here is basically minus 2a comma 2a. This point is 0 comma 2a. This point is 2a comma 2a. This point is minus a comma a. This point is a comma a. This is minus 2a comma 0. This is minus a comma 0. This is 0 comma 0. Then we have a comma 0 and 2a comma 0. Then you have here minus a comma minus a. You have a comma minus a. Then you have minus 2a comma minus 2a. You have 0 comma minus 2a, and here you have 2a comma minus 2a. The respective probabilities are written besides that. So average symbol energy, this is equal to summation m equal to 1 to capital M. You have norm of Sm square into probability of Sm. So norm of Sm squared is basically first, just write it down. Summation m equal to 1 to capital M. Sm1 squared plus Sm2 squared into probability of Sm. Okay, so we have this, and this will be equal to, let's start with this point. So this point has an energy of 2a whole square plus 2a whole square, that is 4a square plus 4a square, that is 8a square. So you have 8a square into its probability is 1 by 12. So 8a square by 12 plus you have here 0 comma 2a. 2a whole square is 4a square by 12. And again you have 2a comma 2a, which will have 8a square as energy into its probability, that is 12. Plus you have here minus a comma a, that is a square plus a square, that is 2a square. 2a square by 18. Plus you have a constellation point here, which again has a comma a, that is a square plus a square, that is 2a square by 18. Then you have a constellation point here, that is 2a square, that is a 4a square by 18. Plus you have this point, that is a square by 18. Plus this is 0. Then you have this point, that is again a square by 18. Plus you have this point, that is 2a square, 2a whole square, that is 4a square by 18. Plus you have this point, that is again 2a square, plus this point, that is 2a square by 18. Plus you have the last row, this one. This is 2a minus 2a comma minus 2a. So this is again 8a square, 4a square plus 4a square. 8a square by 18 plus 4a square by 18. Sorry, not 18, 12. Plus 8a square by 12. Okay. So this, therefore, average energy is, this is 8 plus 4, 12 plus 8, 20, a square by 18, plus we have 18. Yeah, so we have, sorry, this is 12. We have 18a square by 18. So this is 2 plus 2, 4 plus 4, 8, 9, 10, 14, 16, 18. 18a square by 18 plus we have 20a square by 12. So basically we have 40a square by 12 plus a square. This is 10a square by 3 plus a square. This is nothing but 13a square by 3. So this is a standard approach of finding the constellation and average energy of a constellation for a given constellation diagram and the associated probabilities. So coming to Sangeeta's question, how to find average energy of an 8-bit QAM. So QAM is quadrature amplitude modulation scheme. In quadrature amplitude modulation, so okay, so if you look at this phase amplitude modulation, phase shift keying, in phase shift keying you are embedding information in phases. So as you change the phase from this to this, so this is a 45-degree change, you're changing the symbol, so the information is embedded in phase. But in QAM signal, along with phase you have embedded information embedded in amplitude as well. If you look closely, this is also one of the example of a QAM constellation, but it is not your general QAM constellation that you see, which is of generally this form, something like this. So this is your 16 QAM, and 16 QAM you can represent using 16 is 2 to the power 4 bits. So if you have 8 bits, you'll have 2 to the power 8. It is 256 points, and each point will have its energy or Euclidean distance with respect to your origin. So how these points are located and everything matters. Now this is your 16 QAM. Okay, this is a square QAM signal. I can also get a QAM signal. What I'll do is, the first two rows I'll keep as it is, or the middle two rows I'll keep as it is, something like this. Then I'll take these two and put here, these two put here. Similarly, these two put here, and these two I'll, so something like this. So I'll do this. This is also one example of 16 QAM. Both are 16 QAMs. Obviously, this has, yeah. So these are two variations of 16 QAMs. So when you are saying you have 8-bit QAM, which constellation you are referring to? So you have to be very specific of how you are designing the systems. Obviously, we'll go for this kind of systems, but I'm just telling, like, there are variations in QAM. QAM is a very general thing. But what I gave you today is something that is more general and which you can use to find energy of any arbitrary constellation. So maybe I won't recommend you to go for 256, but you can look at 4 QAM, 16 QAM, and all those things, and try to derive average energy for those constellations. I hope it answers your question. If you have any other questions, then please feel free to ask.
Ma'am, I have a question.
Yeah.
So these many things, uh, for exam, we cannot able to do now quickly. So is there any other way to start? We can understand and we can derive this energy.
Sorry, this
We
kind
need to
of,
follow everything.
this
Yeah.
one, this is
So
the
so many
simplest
points
way.
are there. Okay.
In fact, this is a very simplistic form. Actually, when you are going for waveform representation of your signal, you are actually handling things in continuous time. And when you have energy of a signal, if you remember in your signals and systems, it is integral from 0 to some duration, magnitude of x of t square dt. So its equivalent representation when you go for vectorized thing comes out to be simple Euclidean distance. So Anyway, we have brought the complexity down from an integral to a simple Euclidean distance, and this is the simplest thing that you can do. I don't know if there is any other way to simplify it. But obviously, you're not going to get any crazy constellations, which is very difficult to handle. If you see there is a repeatability in this particular constellation, I didn't exploit that. These three and these three have similar things. Then, like these three and these three have similar kind of energies. Similarly, these and these have similar kind of energies. Then you can group these two and these two. These two also have similar energy. So maybe you can try to identify things and reduce your compute. That can be done, but I didn't do it right now because I wanted to keep things very simple. I hope that answers your
Get
question.
it.
Yeah.
Yeah, get it.
Yeah. Okay, if there are no questions, then let me move on to another question. So I deliberately took this particular question in which you are given a particular constellation and you want to identify the number of bits that are used to uh, represent this particular constellation. So as I mentioned earlier, you get a group of you get a sequence of bits. So you get a sequence of bits, you group them in k bits or group k bits, and this gives you m equal to 2 to the power k possibilities, and these are essentially the number of points in constellation. Okay, so m is equal to 2 to the power k is the number of points in constellation. So when someone is saying mpsk, m quam, they are referring to the number of points in the constellation and not the number of bits that are used to represent the constellation. For example, this particular thing that we saw in the very first or this fourth question was an 8 PSK system. So there were 8 points in the constellation. That does not mean that each of these symbol is represented by 8 bits. These are 8-point constellation, and how many bits can you use to represent these 8? Simply 3 bits, because 2 to the power 3 is 8. So when you have 3 bits, you get 8 unique combinations of 3-bit sequences. Okay, so this particular 8 PSK constellation can be represented using 3 bits. So now we'll just have a small glimpse of various classic constellations and see how to get handle over this. So when you have this particular setup, the number of bits, so from this you get the number of bits k as log m to the base 2, and if m is not a power of 2, then we'll use the greatest integer after this log m to the base 2, that is the ceil function. Okay, sorry, the smallest integer greater than this value, that is the ceil function. Okay, so the first example that is given to us is 16 PSK. So 16 PSK corresponds to m equal to 16 constellation points. So therefore you can write m as 2 to the power 4, and what do you have? So k is log 2 to the power 4 to the base 2, which is nothing but 4 bits. Okay. Similarly, when you have 8 quam, 8 quam corresponds to m is equal to 8, that is 2 to the power 3 points in the constellation. So the number of bits k is nothing but log 2 to the power 3 to the base 2. Again, keep in mind the base here is 2 of the logarithm, not 10, not natural log. Be very careful in this business. So this is 3 bits. Whenever you are playing with bits, it will always be log to the base 2. Oh. Then we have QPSK. So QPSK and BPSK are some standard names. Q means quadrature and Q here means you have 4 points in the constellation. So QPSK has 4 points. So M equal to 4 points in the constellation. So just a minute. Okay. Yeah. So you have 4 points in the constellation and therefore number of bits is 2 to the power log to the base 2, log of 4 to the base 2, which is nothing but 2. And finally BPSK is the very primitive, very basic constellation, and this is basically your binary phase shift key. Or BPSK, and for this the number of points or M is 2, which is 2 to the power 1, which means you just need 1 bit to represent BPSK constellation. So number of bits k is log 2 to the base 2, which is 1. Okay. So this is also a very simple exercise, but this basically helps you to relate how bits and your constellations are related. Any questions? Okay, if there are no questions, then let me move on to the 7th question. So the question, okay, so now I'll change the gears a bit and I'll move on to something known as the noise, thermal noise, and all concepts related to that. So it says that consider a receiver operating at 300 Kelvin and bandwidth of 10 kilohertz. Then find the thermal noise floor in dBW and in dBm. So when you have your receivers, you have those electrons that are continuously moving and they vibrate and they produce some heat. And that heat leads to something known as thermal noise, and that gets added to your received signal, which you can't identify, which you can't separate. And this additive noise is the key thing that messes up your communication signal if you are just doing pure digital communication. And we don't have a handle on noise. What we know is just its variance or the thermal noise floor. That's all. We don't have any other knowledge about it, and we can't estimate it. We can't do anything with it. We have to make our receivers that account for this noise, and we need to be careful while designing them. Okay, so this thermal noise floor has a standard formula, which is your KB into B into T. So what are these 3 parameters? So KB is your Boltzmann constant, which is equal to 1.38 into 10 raised to minus 23 square kg per second square Kelvin. This B is the bandwidth of your communication signal, and this T is the operating temperature, or the temperature at which your device is operating at. So this is operating temperature. Okay, so therefore your thermal noise floor so the thermal noise floor is equal to kb, that is 1.38 into 10 raised to minus 23. Bandwidth is given to us as 10 kilohertz, that is 10 into 10 raised to 3 into your your operating temperature is 300 Kelvin. This temperature should be in Kelvin, not in degree Celsius or Fahrenheit. Okay, so be careful in that aspect as well. If it is not given in Kelvin, convert it to Kelvin and then plug it in the expression. Similarly, the bandwidth should be in hertz, not in kilohertz. So first convert that kilohertz into hertz. Okay, so again you will have to use calculators to find this. I'll directly write the solution. So this comes out to be equal to 4.14 into 10 raised to minus 17, but this is in watts. Okay, this particular thing comes in watts. But what you want to do is you want to find it in dBW and dBm. So first we'll do it in dBW. So thermal noise floor in dBW is 10 log to the base 10, 4.14 into 10 raised to minus 17, and this comes out to be equal to minus 163.83 dBW. And thermal noise floor in dBm turns out to be dBW value plus 30, so this is nothing but minus 133.83 dBm. Okay, any questions? Okay, if there are no questions, then let me move on to the next question. So it says that if the minimum received SNR is 5 dB and noise figure is 3 dB, find the receiver sensitivity in dBW. Assume the noise floor as in the previous question. Okay. Okay. So there are three new things that are coming, three new terms that are coming in the picture right now. The first one is minimum received SNR. Then you have noise figure and receiver sensitivity in dBW. And noise floor we already found in the previous question. Okay, so what are these things? So this is a part of link budget that will be looking into a greater detail in the next week. But I believe there are one or two questions which are related to this in your assignment. And a very small glimpse of this was done in either third or fourth lecture. I don't remember exactly when. I think third lecture. Yeah, so what happens is you're transmitting some power, transmitting with some power. So let's say this is your transmit power and this is in dBW. Whatever I'm doing is in dBW. And then your signal goes through certain number of losses. Wireless signal goes through certain number of losses. And these losses come from fading, shadowing, etc. These terms, fading, shadowing, scattering, everything will be discussed in very great detail in the coming lectures. So, right now, you assume like these are some things that are going to degrade the quality of your signal at the receiver. They are going to attenuate the signal strength. Right now, just believe me in that aspect. We are going to understand these fading, shadowing, and all those aspects in very great detail in the coming lectures. The entire course is based on these things. So this is going to degrade your power level, and here you will get PRX in dBW. Okay, so something like this. So this fading and shadowing are in linear scale, those are multiplicative factors. So when you convert it into dBW, you get a subtraction. Okay, and then you have something known as a noise floor. So your signal already has some noise floor, receiver has some noise floor. And this is your thermal noise floor that we obtained in the previous question. But your receiver has amplifiers and other things, filters, amplifiers, and all those things. And those can worsen the impact of your noise. They can enhance the noise, and that enhancement is given by the noise figure. So your noise can be enhanced a bit. So this is your total noise power, and this increase in your noise power is because of noise figure. This also will be discussed in a greater detail in the subsequent lectures. Right now, just believe me that this happens. So this particular thing is basically your signal to noise ratio, or the gap. You receive some signal strength, you receive some power, and you have some reference power. So this gap is basically your, okay, everything is in dBW. So this is in dBW, this is in dB, noise floor is in dBW, and now you have your SNR, signal to noise ratio, that is in dB. So let's say you have this fading and shadowing thing coming up in some alpha. The factor is in alpha. So what happens is, when you're transmitting, okay, first I'll give what happens in linear scale. This part might become confusing when you go from linear to thing. Okay, so linear scale, when you are transmitting with power PTX, is your transmit power. When you see fading and shadowing, your received power becomes alpha times PTX. This is in linear. Okay, and this alpha is less than 1. Okay. then then you have your total noise power, which is your noise floor into noise figure. Okay, so this is, and your signal to noise ratio, I'll just write this as PN. This I'll write as N, and this is NF. Okay, so your SNR is basically your PRX upon your PN. Okay, now let me just take this to the next page as well. Okay, leave it. Here only I'll try to modify it. Okay, so in dB scale, you get PRX as 10 log to the base 10 alpha times PTX. So this becomes 10 log to the base 10 alpha plus 10 log to the base 10 PTX. So this is your fading shadowing alpha thing in dB, and plus you have your 10 log to the base P transmit power in dB. So this alpha in linear scale is less than 1, so essentially this particular quantity is negative. So that's why you get a degradation. So this in dB is negative. So this PRX is basically PTX in dBW minus alpha in dB. Okay. Then you have the noise figure. Okay. So you have this noise figure. I'll just add one page. So noise figure in linear, or noise power in linear, Pn, was your noise floor N into your noise figure Nf. Right. So again, when you convert it to dBW, to 10 log Pn to the base 10, which will be equal to 10 log N to the base 10 plus 10 log Nf to the base 10. So this quantity here, Pn in dBW, will be equal to, this is the noise floor, this is also a power, so 10 log, sorry, your noise power, noise floor in dBW, and your noise figure is a multiplicative gain that is happening. So gains are not a power, those are ratios. So this is noise figure in dB. So here you have your noise floor in dBW. Noise floor is what according to our notations? That is your N. Then this gap enhancement is your NF, and here what you get is noise power, which is Pn. Okay, and your SNR, is your PRX by Pn. So therefore this comes out to be equal to, in dB scale, this is in linear, 10 log SNR to the base 10, which is 10 log PRX by Pn to the base 10, which comes out to be equal to 10 log received power to the base 10 minus 10 log PRX to the base 10. This is equal to your PRX in dBW minus, this is Pn, sorry, your noise power in dBW again. SNR is a ratio. So this SNR in dB. Okay, now you have this PRX in dBW. Plus, yeah, you have this PRX in dBW, and you have this noise power in dB. So the difference in these two is basically your PRX minus your Pn, which is essentially your SNR in dB. So this gap is your SNR in dB. So now what is given to us in the question? So I hope that you understand noise figure and PRX, PTX and all those things. So now what is given to us is your minimum received SNR is 5 dB. So the minimum received SNR that your device can sense, or rather, sorry, the minimum received SNR that your communication system receiver is able to see. So given minimum received SNR or SNR is always at the receiver. Minimum SNR in dB, that is SNR min in dB is 5 dB. And what they want to ask is, if you have the thermal noise floor as in the previous question, and if you have your 3 dB ka noise figure, then what is the minimum receiver sensitivity of your system? So minimum receiver sensitivity is what does it mean? What is the minimum value of this PRX that your receiver can sense? So minimum, or rather receiver sensitivity, that is your PRX min in dBW, is the minimum value that the receiver can sense. So if I plug in SNR min and PRX min in this particular equation, what will I get? So what we have is SNR min in dB is nothing but PRX min in dBW minus your PN in dBW. So your receiver sensitivity, therefore receiver sensitivity PRX min is given by your PRX min in dBW, which is SNR min in dB plus you have your PN in dBW. Now I'll SNR min in dB remains as it is, plus this noise power is summation of two quantities, like this noise floor in dBW and noise figure in dB. So this I can write as your N in dBW plus your noise figure in dB. So what is the value of minimum SNR? Minimum SNR given to us is 5 dB. So this is equal to 5 dB plus the noise floor that we have obtained in the previous question is minus 163.83 dBW. So this is minus 163.83 dBW. And what is the noise figure given to us? The noise figure given to us is 3 dB. Yeah, okay. I think I made some mistakes in my calculation. So when you use the calculators, you get 5 minus 163.83 plus 3, and this comes out to be equal to minus 155.83 dBW, and your receiver sensitivity in dBm is simply this quantity plus 30, so that comes out to be equal to minus 125.83 dBm. Is it clear? Any questions? Any questions in this particular receiver sensitivity part? Okay. Okay. If there are no questions, then let me move on to the next question. So this is the question, or this is some concept that was discussed in the briefly in the lecture, like how long your phone battery lasts. And I was able to see one or two questions related to this in the last year and this year's assignment as well. So I thought, why not just take up one example of this so that it helps you out to figure out what exactly is happening. Okay, so what is given to us is, consider a battery with 5000 milliampere hour battery of the mobile phone. Suppose the phone draws 30 milliampere in idle mode, like when there is no call, it is drawing 30 milliampere of current, and in idle mode, and when there is no when it is in idle mode and there is no call, it is drawing 30 milliamperes of current, and when you get a call, the phone is drawing around 100 milliampere hours of current, and it is given that in every hour it receives two calls, and each of these calls are of 5 minutes and 3 minutes duration. So if this is the situation, then how long is your battery life or battery going to last? So what is given to us is, the first thing is total charge in the battery, that is 5000 milliampere hour. Then what is given to us is, when current drawn in idle mode, let's say it is I, and that is 30 milliampere, and current drawn in call mode, that is IC, that is 100 milliampere hour. So the duration of call in 1 hour, so this is, let's say, TC, and we have 5 minutes and 3 minutes, so 5 plus 3, that is 8 minutes. So you have 5 minutes plus 3 minutes, and if I convert it into hours, that is by 60, so this is nothing but 8 by 60 hours. And idle duration per hour, this is 1 minus TC, that is 52 by 60 hours. Okay, so this is the situation. So therefore, the charge consumed per hour is the charge per hour in idle mode plus charge per hour in call mode. So this is basically TC into IC plus TI into II. So this is, let's say, C total. So therefore C total is TC is what? It is 100 milliampere into 8 by 60 plus 30 milliamperes into 52 by 60, and this comes out to be equal to around 39.33 milli yeah milliampere millicoulomb per hour. Yeah. So therefore the battery life is total charge in the battery divided by C total, that is the total charge consumed per hour. So total charge in the battery was 5000 milliampere hour, and yeah, this was in milli. And then you have 39.33, and this comes out to be equal to 227.12 hours. Any questions? Okay. If there are no questions, then let me move on to the last question that I have planned to cover today. So it says that consider a 4G device using 32 comm modulation transmitting at a rate of 12 Mbps. Assume the Nyquist pulse shaping is used, then the duration of comm signal is. So it is asking is what it is asking is what is the duration of one comm signal. So what we want to find is what is the symbol duration TS in this setup. Okay, so symbol duration TS is basically 1 by symbol rate. This is because your symbol rate and bandwidth are same because you are using a nice twist pulse shaping filter. Okay, so you have this particular setup now. So what we want to first find out is what is the symbol rate. So this results in a question of what is symbol rate. By definition, this is number of symbols transmitted per second. Okay, what are we given? We have a 32 comm. So we have 32 comm signal, which means we have m equal to 32 points or 2 to the power 5 points. So the number of bits required to represent one symbol or number of bits per symbol are log m to the base 2, that is 5. Okay, so 5 bits correspond to one symbol. Then what is given to us is the data rate is 12 megabits per second. So these are the number of bits that are transmitted per second. So how will we get symbol rate? So symbol rate will be equal to number of bits per second into number of symbols, sorry, wait, upon number of bits per symbol. So that will give me symbol rate in symbols per second. Okay. The numerator is your data rate, that is 12 megabits per second. That is 12 megabits per second, and the number of bits per symbol are 5 because we are using 32 comm. So this is 5. So this is nothing but 12 by 5, that is 2.4 mega symbols per second. Okay. Therefore, the symbol duration TS is 1 over your symbol rate, that is 2.4 into 10 raised to 6, which is nothing but 0.42 microseconds. So I think some similar questions you have in your assignment as well for Nyquist pulse shaping filter and all those things. So this is how it goes around. Any questions? So this was the last question that I wanted to cover today. If you have any questions throughout the tutorial, feel free to ask. Before I stop, again some quick logistics. Every week, Saturday 5 p.m. to 7 p.m. I'll take this tutorial. I'll focus on that particular week's content. Second thing, after every tutorial, the recorded video of this particular session will be up, of that particular session will be uploaded to my YouTube channel, and the playlist which will have those videos, I have given its link in the comment box, in the pinned comment. Second thing, these links will also be shared to you from by the NPTEL people in an Excel sheet, and in that Excel sheet there will be an additional folder link which will give you access to these slides or these notes that I have just created in this session. So this also you will be able to access. And one final thing, if you have any questions or after this session has ended, there is a Q&A portal in your NPTEL setup. You can post those questions mentioning that these are for TA session or something like that. So I will look at those questions and take up those questions in the next TA session before starting with that particular week's content. I won't solve the questions related to your assignments right now. For those assignment questions, towards the end of your course, I will take one summary session. In that, I will take up all the doubts related to assignments as well, or any additional doubts that are related to this particular course. But as long as the deadline of assignment is not done, I won't be solving those questions. Okay, any other questions for today's session? Okay, if you don't have any questions, then feel free to leave the meeting, and thank you for attending today's session. If you want me to go slow or go a bit faster, please let me know. It will be easy for me to carry forward. I hope you liked the session. Thank you for coming today. Hope to see you in next week as well. Thanks.
Thanks. Hello, ma'am. Hello.
Yes.
Actually, when the recorded videos are told about the E not B calculation, you know,
Yeah.
yeah. So that I didn't get it how to solve that one. So that if you given any idea for next week,
I'll
it will
do
be
it
good,
in
ma'am.
next week. Yeah, I'll do it in next week. Yeah.
Thank,
Sure.
thank you.